Hi everyone, welcome to Virtual School. Physics is fun. Wan Liao says hello. Okay, today I'm going to teach you about forces acting on a person in a lift. In another word, the normal reaction force, R, which we have learned earlier on. Okay, now how do we take our weight? How do we measure our weight? Of course, by standing on the weighing scale. Okay, if we step on the weighing scale, the reading of the weighing scale shows our weight. Now, the reading of the weighing scale actually shows the normal reaction force. Now, under normal condition, our weight is equal to the normal reaction force. Okay, so we stand on the floor, our weight is acting downwards, normal reaction force is acting upwards. So it's a reaction force of our weight. So this normal reaction force is the reading of the weighing scale. What if we bring the weighing scale into a lift, okay, and see what happens? So if the lift is not moving, it is stationary, and we step on the weighing scale, of course, the reading of the weighing scale, it will be the same as our weight. All right, so R equals to W because it is just like when we were outside. What happens when the lift start accelerating upwards? Okay, now the lift is accelerating upwards. So by using Newton's second law, F equals to ma, we know that the lift is accelerating upwards. All right, and net force is always the same direction as the acceleration. Okay, because net force is the one that causes this mass to accelerate. So obviously the net force and the acceleration, they are always in the same direction. Now let's look at net force. The net force is made up of the normal reaction force. Normal reaction force is upwards. Okay, so which is the same direction as the F, the net force. Therefore, the R is positive. But the weight is acting downwards, so it's in the opposite direction, therefore it is negative. The direction of the weight is negative. So from here we write the net force, so we know that the net force will be equals to R plus negative W. In another word, R minus W equals to MA. By bringing the W over to the right side, so we get R equals to W plus MA. So that means to say the normal reaction force will be more than the normal weight, our actual weight, when the lift is accelerating upwards. Okay, is it always this case? If the lift, after accelerating upwards, it moves with constant velocity. So if constant velocity means acceleration is zero, yeah, acceleration is zero. So using the same formula as just now, F equals to ma, W minus W, R minus W equals to ma, bringing the W over, so we get R equals to W plus ma. But the A is zero, so therefore R equals to W. So the reading of the weighing scale goes back to the normal, yeah, normal reading, which is the weight, our weight. Now, if the lift is decelerating upwards, yeah, before it stops, it has to decelerate. Okay, so now the acceleration is negative. So by substituting the A with negative, so we will get R equals to W minus MA. Same formula, huh? All these are the same formula as just now. But now A is negative, so that gives us R equals to W minus MA. Means what? Means R is less than W now. So the reading of the weighing scale now is lower than our normal rate. Okay, so you see the reading of the weighing scale changes depending on the state of motion of the lift. If the lift is moving downwards now, it is moving downwards with acceleration. Yeah, it is accelerating downwards. So what happened? So same, we use Newton's second law, F equals to ma. So now the A is downwards. Yeah, A is downwards. And of course, the net force is also downwards. Okay, F and A is always in the same direction. So now our W is downwards. Therefore, W is positive. But R is in the opposite direction. So R is negative. Okay, so R is negative. So W minus R equals to MA. So when we rearrange, we get R equals to W minus MA, meaning R is less than W. So again, the reading of the weighing scale is less than our normal weight. So if the lift is moving downwards with constant velocity, so again, if it is constant velocity, acceleration is 0. So R will be equals to W minus 0. So R equals to W. If it is decelerating downwards, yeah, so decelerating downwards, so the acceleration is negative. So substitute A with negative. So W minus R equals to M bracket negative A. So by rearranging, so we get R equals to W. Bring this over, so we get plus, right? So this negative here, when we bring over, becomes plus. So R equals to W plus MA. Wow, R is now more than W, right? So we see here when the lift is moving upwards or downwards, yeah, accelerating upwards or downwards or moving with constant velocity, so the R will change accordingly. All right, so this is a summary. So if the lift is moving upwards with acceleration A, so our R will be more than W. If it is moving with constant velocity, R will be equals to W. But if it is decelerating upwards, then R will be less than W. The motion downwards will be opposite to the motion upwards. Yeah, downwards with acceleration, it will be R less than W. When it's moving with constant velocity, R is always equals to W. Now moving downwards with deceleration, so R will be more than W. Okay, so R changes according to the state of motion of the lift, meaning to say the R will change according to the motion of the person. Now, what if the lift that is traveling, unfortunately, the cable that holds the lift snap, it breaks. Obviously, it's going to drop, right? So it drops with uh, gravitational acceleration. So now it is moving downwards with gravitational acceleration. So here, so the cord snaps, the lift accelerates downwards with gravitational acceleration. So using F equals to ma, so the W is downwards, so W is positive. R is upwards, so R is negative. Therefore, W minus R equals to ma. Rearranging it, R equals to W minus ma. But now our A is G, is gravitational acceleration. So now W minus mg. W minus mg is our R. But what is W? W is also mg, right? W weight is the gravitational acceleration acting on the mass. So R equals to mg minus mg equals to 0. So what does it mean? That means to say the reading of the weighing scale is 0. So the reading of the weighing scale shows the weight, right? So now this scenario is called weightlessness. Weightlessness. Yeah, so there's no weightlessness. So the lift is undergoing free fall. So this scenario tells us that if a person is falling under free fall, falling under the pull of gravity only, okay, so the person will experience this scenario called weightlessness. Yeah, zero weight, no weight at all. Okay, so this is our lesson for today with regards to forces acting on the person in the lift. All right, so we will continue with the pulley system. So watch out for more videos. Thank you for watching. Bye.